Okay, we're going to continue on here with what we've been talking about, which is bonding. So last time we sort of finished up and we're in the middle of some examples of how to sort of correctly draw Lewis structures. Again, when we go to draw Lewis structures, there's really several steps that you kind of want to follow, especially when you're drawing it for covalent compounds. And again, if you sort of follow these steps, should lead you to a pretty good structure when it's all said and done. Really, one of the first things you want to figure out is sort of the skeletal structure, basically how it's put together. And as we talked about last time, typically speaking, in the center spot is the least electronegative atom. We also don't typically find fluorine, which is the most electronegative atom in the center. And we also don't find hydrogen in the center, again, because obviously it would have more than 2 electrons, which it cannot have. The next really most important thing is really the total number of valence electrons. So you want to count up the total number of valence electrons. Remember, if something does have a charge, you do need to adjust the total count so you don't end up short or without too many. And again, if something obviously has a negative charge, that means it should have more electrons. So you need to kind of add it to your total. Something has a positive charge, then it has lost electrons. So you need to basically subtract it from your total. That number, as we talked about, is really important because when you're done with your picture, it's got to be exactly that number to the exact value. It can't have any more or any less. The next best thing to do at that point is just to draw a single covalent bond, which is basically a line from the center atom to each of the outside atoms, remembering that each line basically represents 2 electrons. You could then really count off from your total electrons, how many electrons you still have to place on the structure. Then all the rest of the electrons go on the outside atoms first. And they do go on as pairs of electrons, so dots, until basically all the atoms on the outside have 8 valence electrons, unless obviously it's hydrogen, then they should get no dots. If at that point you basically fill up everybody on the outside with electrons and you still have electrons to go, then you go to the center atom and you also place them as dots as well there on the center atom. At that point, if you find yourself on the center atom placing dots, you should be out of electrons at that point, hopefully, and you should have placed pretty much all of your electrons. If at that point you've distributed all of your electrons, the last thing you really want to do is make sure that everybody has met the octet rule. And it's really at this point, as we talked about, that if the octet rule is not met, this is really the place where you should try to fix it. And you should try to fix it by making double bonds or triple bonds. So if the octet rule is not met, then you really should try to fix it by making a double bond or a triple bond if necessary. As we talked about last time, you kind of want to exhaust all your double bond possibilities. And then if it still really doesn't fix it at that point, then you really should go to a triple bond. Remember, though, that when we do make a double bond, what we're doing is really taking a pair of electrons in to make that double bond. We just don't draw the double bond. We just don't put extra dots. So we're bringing those electrons in to do so. And again, if you sort of follow these structures, should really hit you a pretty good structure when it's all said and done. As I mentioned last time, you know, pretty much don't want to kind of double bond and triple bond really right out of the box and stuff like that. So in most cases, what you want to do is really kind of save it for a situation where you do need to maybe fix it. And then you'll usually end up with sort of hopefully the right structure. Again, if you do it sort of in piecework where you think about each individual element sort of separately and how many electrons they have, and how many they need to get to 8. A lot of times in my experience, people will end up with really the wrong structure, too many bonds, not enough electrons. So it's best if you sort of follow these. And again, as I mentioned, sort of think of the total electrons as just, as many electrons you need to distribute to everybody in the entire molecule by following these rules. Any questions on any of those things there? All right, so we were drawing some, I think, last time, yes, some of these. Did you need more time to draw some of these, or are we good to go through them? Yeah. All right, so why don't we go through these here, and again, make sure everybody's on the same page. Actually, why don't you take 5 or so minutes here or finish up if you needed to, and then we'll go through them here. So why don't you take a few, just in case you weren't done. No, we're kind of in the middle there last time. Okay, so let's start taking a look at some of these. We'll start the first one here, which is SH2. So again, I'm just going to start with the total number of valence electrons. So that is equal to the group number. So there is 1 sulfur at 6. There are 2 hydrogens each at 1, which means my picture here should obviously have 8 valence electrons. We have sulfur and 2 hydrogens, so clearly hydrogen cannot be in the middle. So it's got to be sulfur there in the middle. Hydrogen will be on the outside. Again, we're just going to do a single bond from the center to each of the outside ones there. That is a grand total of 2 and 4 electrons that have been used. We have 4 more to go. Can I put dots on the hydrogens? I cannot. So really, I now need to go to the center atom. Go into the center atom. That's 2 and 4. That's now a grand total of 8 electrons that I put on there. The sulfur in the middle has 2, 4, 6, 8. Each of the hydrogens have 2, so that is good. Yes. Any questions on that one there? Looking at NH4 plus, nitrogen is 5. There are 4 hydrogens each at 1. In this case, we do have a plus, which means that it has lost electrons. That means we actually need to subtract 1, so we get the right count there. That is also going to give us 8 valence electrons in this case. Again, here, clearly, nitrogen's got to go there in the middle. Hydrogen will go around. 1 single bond from the center to each of the outside atoms. That gives me 2, 4, 6, 8, and that is all we write on this one here. We are good. We got hydrogen each has 2, and then obviously our nitrogen there in the middle has 8. Again, we typically do put brackets around something that has a charge and the charge on the outside. Any questions on that one there? Rolling to HCN. Yeah. We subtracted 1 because this is an ion that had a positive charge. So the only way somebody gets a positive charge is that they lost electrons. So you have to subtract off an electron from your total there. Otherwise, you'll have too many. Yeah. Just like if we had a negative charge, that meant that somebody has gained electrons. So you need to add electrons to the total to accommodate for the charge. Other questions? Okay, so here we got hydrogen, that's 1. We got carbon, that's group 4. And we got nitrogen there, which is 5. That looks like 10 valence electrons. In this case, hydrogen will not be in the middle. So it's between carbon and nitrogen. The one should go in the middle should be carbon. Again, it is less electronegative, further to the left on the periodic table. So we will have an H, a C, and an N. We're going to follow our same procedure here. A single bond to everybody gives us 2 and 4 electrons. We got 10 total to go, or 10 total. So with that's 6 more to go. We cannot put it on the hydrogen, so we'll put them on the nitrogen here. So 2, 4, and 6 at this point. We have now distributed all 10 electrons. Is everybody good in this picture? No, the one that is not good is carbon, right? Carbon in the middle there has only 2 and 4 electrons. So we could try to fix it by making a double bond. So again, what we would be doing is taking a pair of electrons in to make that double bond. And if we do that, we will end up with something that looks like this. Is carbon good now? It is not. It got better. It now has 2, 4, 6 electrons around it. There's really nowhere else we can make a double bond, as we cannot double bond to the hydrogen. So the next choice at this point is to go to a triple bond. And a triple bond works the same way. We're going to take another pair of electrons and basically bring them in to make that triple bond. And we will end up with HC triple bond action happening there. Now is the carbon good? Carbon is good. It's got 2, 4, 6, 8. The nitrogen is good as well. 2, 4, 6, and the 8 with the dots on the outside. Hydrogen still has 2. And again, we have a grand total here of just 10 electrons. Any questions on that there? All right, last, yeah. Yeah.
That's the final answer. So if we're just the right
That's, so are you asking if you stopped at this structure? Is that what you're asking? If you stopped at that structure right there, it would be considered wrong. And it would be considered wrong because the carbon did not get the 8. So it's still short. And remember, the goal really of all bonding is really for everybody to get to that 8. So they become like the noble gases. So technically, the octet rule does need to be met for everybody except for hydrogen, that only needs 2. Yeah. So yeah, so you do in this case, to get the correct structure, it has to go to that triple bond. Yeah. Other questions? Okay. So looking at SO4 2 minus, here we have sulfur, which is 6. We got 4 oxygens, which are also 6. Here we have a -2, which means that it has gained 2 electrons. So in that case, what we need to do here is actually add 2 electrons to our total. Because of that, that's a lot of mass. That's 24, 30, 32 perhaps. Let's go with that. 32 valence electrons here. We have sulfur and oxygen. Again, we have 1 sulfur, 4 oxygen. So sulfur should be in the middle. It also is, if you look on the periodic table, sulfur is below oxygen, which means it's less electronegative. So again, should be in the middle. We will have our oxygens all around here. And again, we're going to do a single bond to everybody. That is 2, 4, 6, 8 electrons. Leaves us a lot more to go there, the 24 perhaps. Those are going to go on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 at that point. At this point, every oxygen has 2, 4, 6, 8. They're all pretty much identical to each other. Sulfur in the middle has 2, 4, 6, 8. Put a little bracket around it to make it look all nice. And there it is. Yes. Yes, sir. Was that? There should be 32 electrons, I believe, right? At this point. Do we have 30 on the picture? No, there's 32. So there should be, there's basically 8 there, right? I might got ran in up here. There should be those 2 dots up there. Yep, there you go. Yep, no problem. Other questions? Yeah. Yeah, you should. It's common for anything that has a charge. You should put the brackets and the charge on the outside. You know, so I'll say yes, you should do that, I suppose. I'm probably more interested in the picture inside, but you know, to finish it out correctly, you should kind of put the brackets. The brackets means it's something that has a charge as an ion. So since we really don't in this class go through the process of figuring out exactly where the charges are in the actual picture, it's very customary just to kind of put brackets and go, overall, this thing has a -2 charge. In reality, what's really happened in this particular one is each of the oxygens is actually carrying a -1 charge. The sulfur in the middle actually has a +2 charge in this sort of situation. And that's where the -2 charge overall comes from. But since we actually don't go in that calculation, just to generically put the brackets and the overall charge is what we typically do. Are you asking, can you draw it a different way with like double bonds? Is that what you're asking? No, so if your question is connection wise, it should be connected like this with the sulfur in the middle and everybody connected to it and stuff like that. Yeah. Other questions? Okay. I'll hold off on answering the yes part in a second. I guess whoever just said that. Yeah. And why you shouldn't do it in this class in terms of double bonds and stuff like that. Okay. So let's take a look at this last one here, which is nitrogen, which is N2. N2 is 2 nitrogens, which is 5, which is 10 valence electrons. In this case, there really is no center atom. There's just 2. It's a diatomic molecule. So normally we just kind of send those guys side by side. And we still can follow the exact same sort of procedure, even though there's really no 3 or more or center atom. We're going to make a single bond. That gives us 2. We got 8 more to go. We'll go on one outside guy here. That is 2, 4, 6, and then 8. At this point, we have distributed, right, all of our 10 electrons. Nitrogen on the right's good, but here the nitrogen on the left is short. So we could try to fix it here by making a double bond. So we'll bring some electrons in. That will then give us a double bond in the middle. That looks something like this. Did that fix it in this case? It did not. Again, the nitrogen got better. It got to 6. So we have to, again, here go to a triple bond. And this is why nitrogen is actually triple bonded. Got to bring those electrons in to do that. And we will end up with an actual triple bond here that looks something like this. Yeah. Any question on the steps to drawing Lewis structures? Again, you can see hopefully in these examples, we kind of save our double bond, triple bonds to fix things if necessary. And that's probably appropriate for our class in here as to how to do it. Any questions on how to draw? Okay. Also, one point on drawing these things is everybody here will obey the octet rule. So everything that you will be asked to draw in this class will obey the octet rule. We're going to talk about here in just a second some exceptions to the octet rule, but everything that you draw in here should obey the octet rule. All right, so we saw a little bit about resonance last time when we were drawing some of those pictures, but let's talk a little bit about bond length first. Bond length is really the distance between 2 atoms, obviously within a bond, between really the nucleuses in those guys. And there is a general trend, and by no means do you need to memorize these numbers or anything like that. So they're just up here to illustrate some points. If we look at the bonds between carbon and carbon, we have basically our single bond, our double bond, and our triple bond here between carbon and carbon. And what we see in terms of the bond length is very common of what we actually do see as we start making bonds. The single bond is 154, the double bond is 133, and the triple bond is 120. What we see is the length of the bond actually starts to decrease as you keep adding basically another bond. So as we saw when we were drawing our Lewis structures to make like go from a single bond to a double bond, we're bringing electrons in, and what that does is sort of bring everybody together a little bit closer. You go to make a triple bond, everybody again gets moved sort of closer to each other. So the single bond is sort of the longest, if you will. As you drop a double bond in, people move closer. Triple bond, everybody moves closer. Carbon and nitrogen, same trend that we see here. 143 for single, which is longer than our double bond, which is longer than our triple bond. How that relates to bond strength is a triple bond is much stronger than a double bond, and a double bond is much stronger than a single bond. They're not like twice as strong or 3 times as strong, but that's the general trend that we see. So the general trend that we see for length is single bond is longer, double bond gets smaller, triple bond gets smaller. And what we see for strength of those bonds is triple bond is the strongest. I sort of relate it to like if you grab a brand new pencil out of the box, it's nice and long. You could take that thing and snap it pretty easy. You take a couple of chemistry tests, you're down to like an eraser and a nubbin, right, of a pencil. Very hard to try to break that thing in half or anything like that, because everything is obviously much closer together and held a lot tighter. And that's sort of what happens with the bonds as well. As the thing starts to shrink, it takes a lot more energy if you want to try to break a triple bond versus say a single bond. Any questions on that there? So we talked about resonance when we were drawing some guys last time, but remember a resonance structure is really multiple sort of Lewis structures that you could draw for a particular compound. And it's really happens in a situation where, as we saw, say with carbonate, I think is what we drew, you had sort of options as to where you could have put the double bond. And you could basically draw, you know, the picture with the double bond, say upwards, or the double bond to the left, or the double bond to the right, like we did. And each of the structures by themselves are legitimately good structures, but they are related to each other as what is known as resonance structures. And really the reason for that is if we kind of think about our carbon dioxide, our carbon, not dioxide, carbonate example here. You know, when we think about those double bond electrons that we're bringing in to sort of make that double bond, as I mentioned, I think the other day, you know, at any given point in time, those double bond electrons could kind of be to the oxygen on the left, but then they may kind of move over to the oxygen up on top, or they may move themselves over there to the oxygen to the right. So again, they were sometimes referred to as being delocalized, kind of moving around. And the true structure is probably somewhere between all three of those that we, for example, we drew for carbonate, as those electrons are moving around. So if you're asked to sort of draw a resonance structure, you know, the basic way that you do that is basically think about, okay, I put the double bond here, but maybe I could have put the double bond over here, or maybe I could have drew the double bond over here. And you could draw some different structures that are basically equivalent to each other. And here's that carbonate example here. You don't have to worry about the charge, but by the way, that is where the -2 charge actually comes from. It's actually on those two oxygens that are there. But again, any one of these guys would have been an acceptable sort of Lewis structure for carbonate. But if you're asked to draw the resonance structure, you actually would draw them all. I personally am probably not going to ask you to draw too much resonance structures, but that is what it means. A benzene ring is actually an organic molecule. It's basically 6 carbons in a ring structure. Each of these things are carbons at the end. And it basically has 3 double bonds within the ring. And you can sometimes draw benzene that looks like this, or the double bonds can be moved around. And a lot of books and people will sometimes even just draw benzene with like a circle in the middle to indicate that those double bond electrons basically are moving around the ring. So it's a very common sort of way that this is sometimes drawn. That's more of an organic compound, which we'll get into a little bit of organic at the very, very end of the class, but you know, you'll sometimes see benzene drawn. Now, let us talk about, and like I said a second ago, you know, if you're not asked to draw the resonance structure, you don't have to draw them all. So only if obviously you're asked to draw a resonance structure. What I just said when we were talking about drawing these Lewis structures is everything that we draw in here should 100% obey the octet rule. But there are exceptions to the octet rule where maybe the octet rule is not met and it is an okay situation. So for our purposes here, what you need to know is just what the exceptions are. You won't be asked to draw any of the exceptions, but you just need to know basically what the kind of exceptions to the octet rule are. So the first real exception to the octet rule is what is referred to sometimes as an incomplete octet. And an incomplete octet, basically, much like the name sounds like, incomplete means it did not get to 8. And there are certain things that are just perfectly fine with not getting to 8. The 3 main guys that do that is beryllium, aluminum, and boron. And in terms of covalent bonding, it is really boron that happens a lot with. And boron, for example, is what is sometimes referred to as being electron deficient, and it's perfectly fine with that. And it just needs to get to 6, actually. So something like BF3 if we look at the correct drawing for it, is this. And if we count the electrons again around our boron, it actually only has 6. It did not get itself to the octet rule. Everybody else there did. Fluorine got itself to the octet rule in this structure, but boron did not. And again, is perfectly fine with that. And this was referred to as being an incomplete octet. And in the future, if you continue to take chemistry, that's probably the main element that you will see that sort of happen to. Again, in here, we won't have any incomplete octet, but that's one of the exceptions to it. Another exception to the octet rule is what is sometimes referred to as an odd electron molecule. And these are guys where when you add up the total number of valence electrons, you end up with an odd number. Now, our way that we draw those structures is basically to pair off electrons. So obviously, if you end up with an odd number, you are going to end up with basically one unpaired electron. You may have heard of maybe free radicals. Yes, free radicals are basically these guys. They have one unpaired electrons. They are very, very reactive. A lot of that happens in like atmospheric chemistry with chlorine. They're very reactive because frankly, they have one electron. They're not very happy about that. So they want to kind of fix that. So they start reacting, relatively quickly. NO is an example of that. NO2 is also an example of that. Again, you can see you kind of end up with one unpaired electron. So incomplete octet is an exception to the octet rule. An odd electron molecule is also an exception to the octet rule. If you continue on with chemistry here, I don't know what the number is. Is it 1A maybe here at this school? You will come across this exception to the octet rule, which is the major exception that we do see a lot. Not in this class, but if you continue on to kind of the first semester general chemistry 1-2 course, you'll see it. And that is what is referred to as the expanded octet. The expanded octet, also much like the name implies, is when somebody goes over 8 electrons. And there are certain elements that have the ability to go over 8 electrons. We could get upwards of 10 to 12 electrons around it, and it's perfectly good to do that. So right there on the periodic table where you see our good friend sulfur, if you go to sulfur to the right, to the left, and like down, those are the guys that actually do have the ability to do the expanded octet. The reason for that is when we look at the periodic table at our friend sulfur, it is in what period is sulfur? Is in period number 3, which means it's on n is equal to 3. On the third energy level, what orbitals do we have? We have s, right? We have p, and that is where we first start to see d's occur. So although they may not be using those d orbitals, they do have the d orbitals available to them to sort of stash the extra electrons in. And that's why they have the ability to do that. That is also why when you look at something like carbon, nitrogen, and oxygen, which is above that in period number 2, they do not have d orbitals, which means they can never, ever go over 8. They got to always obey the octet rule no matter what situation. So sulfur and those guys can go above the octet rule, which when we go back to our drawing here of sulfate. In this class, you should draw sulfate like this, like we just did with the single bonds because it does obey the octet rule. But in reality, if you Google it and then draw this, people know you Googled it, because you're supposed to obey the octet rule and you clearly did not by doing this, right? Which is why you should never always take an answer you see online, because you might be right, but it might be wrong for your situation. Yes, this is an acceptable and actually a better picture for sulfate with the double bonds. In this particular case, the sulfur has 2, 4, 6, 8, 10, 12 electrons around it. For reasons outside of our class, it happens to be in this case, this is a much better picture actually than this one. But for our class, you should end up with this picture because that obeys the octet rule on the left-hand side. So if you were asked to draw sulfate, you should end up with the picture on the left, not the one on the right, even though in real life, the one on the right is actually the much better picture. But we didn't talk about why that's a better picture in this class, so you shouldn't end up with it. Any questions on that? Obviously, the one on the right is an expanded octet situation. The one on the left obeys the octet rule in terms of sulfate. Any questions? Okay, so once again, you should always draw things in this class obeying the octet rule. In terms of the exceptions to the octet rule, you just need to know what the 3 exceptions are: expanded octet, incomplete octet, and odd number of electrons. Any questions? All right, so we're going to then talk about geometry here of these molecules. And molecular geometry refers to the 3-dimensional arrangement of the atoms in a molecule. We can really kind of look at a Lewis structure and look at the central atom and predict sort of the geometry. When we do geometry, it is always about the center atom. So that's always the most important one. It's always the center atom that you want to focus in on. Nobody else is that important. And we're going to talk about really 2 types of names here when we talk about geometry. One is sometimes referred to as the electron pair geometry. And that basically describes how the electrons are arranged in 3-dimensional space around the central atom. The other name for geometry that we're going to talk about is what is sometimes referred to as the molecular geometry. Or sometimes people call that one like the shape of it. And really based on the electrons that are around the central atom and really the type of electrons that are there, bonding electrons, non-bonding electrons, it can have an effect on the overall actual shape of the molecule. And that is what is known as the molecular geometry. So we're going to talk about 2 different names as we kind of go through this. Again, one is the electron pair geometry, one is the molecular geometry, or the shape of it. This is the basis of this approach is what is referred to as the valence shell idea. And really, when we think about bonds, they are obviously made up of electrons, which are negatively charged, which ultimately means negative and negative things really don't want to be near each other. The problem is they got to be near each other to keep everybody together in the bond. So they try to do the best that they can to pretty much get as far away as possible and keep themselves at a nice distance that they could sort of be happy with. So as these electrons sort of move, anything that's bonded will kind of move with it, and they will kind of come to rest at a, as far away as they can kind of get from each other in a particular situation. This is what is sometimes referred to as the valence shell electron pair repulsion model, hence why they abbreviate that thing. That is a mouthful. It's basically divided into 2 types of categories. Basically, that is guys where the central atom has no lone pairs. That basically means when you draw your Lewis structure, there's no dots on the center atom. And there's ones where they do have lone pair or non-bonding electrons. That means when you draw your Lewis structure, the center atom has some dots on it. There's really one major thing that you need to keep in mind when you're doing geometry, and that is that if you have a double bond or a triple bond, it basically counts as 1 electron pair and 1 bond. So that's really important when you're doing geometry. Any type of double or triple bond, when you look at it, counts as 1 electron pair and 1 bond. And that's because even though it's a double bond, triple bond, it's basically effectively moving as like 1 unit, basically, that's happening there. So that's why we sort of treat it as 1. The second thing there, not too important for us because we're probably not going to do a lot of resonance structures, but if you drew a resonance structure for a particular molecule and it was possible to do so, you could apply this geometry, and if you did everything correctly, you will end up with really the same geometry for each structure that you drew. Again, if you sort of drew everything correctly. All right, so let's take a look at the simplest thing that you could ever have, which is a diatomic molecule. And the diatomic molecule obviously has only 2 atoms. There's no central atom, basically 2 atoms. Whenever you got a diatomic molecule, it is going to be linear. Don't even think about it. It doesn't matter if it's 2 of the same. Doesn't matter if it's 2 that are different. The geometry is going to be linear. Doesn't matter if you got like a double bond, going to be linear. Doesn't matter if you got a triple bond, also going to be linear. So the geometry for anything when you basically only have basically 2 atoms involved is always going to be linear. Like 2 points can only be basically put on a straight line, right? So basically that is what's going to happen here. They're going to be on opposite ends of each other basically within a straight line. So that is like the simplest thing that you could get is linear, and it always occurs, and it always is a geometry when you have only 2 atoms involved. When you have 3 or more atoms, you need to really look at kind of 2 things is really important. So when you have 3 or more atoms, you want to first look at always the center atom and basically how many electron pairs. So when you look at the central atom, you want to count up the total number of electron pairs. Doesn't matter if they're dots, doesn't matter if they're lines, bonding, non-bonding electrons. You want the total number of electron pairs there are. Again, if you have a double bond or triple bond, it would only count as 1 in that situation. The other really important thing to think about is basically the number of bonds there are to the center atom. So really, if you know the number of electron pairs, that's pretty much all you need to know to figure out the electron pair geometry name. If you know the number of electron pairs and how many bonds there are, that's all you really need to know to figure out really the molecular geometry sort of shape. The best way to do this is to kind of make a table, maybe make a table at the end here as we go through. We'll kind of make a pseudo table there. And to really memorize it. Most people can't 3-dimensionally see it in their head. Me either. I can't either. So, the best thing is to draw a correct Lewis structure, count up the electron pairs, count up the bonds, and go, okay, I got 3 electron pairs. That's this geometry. 3 electron pairs, 2 bonds. That's, this molecular geometry. So let's take a look at our first sort of example, which is beryllium chloride. It is an incomplete octet. And if we look at the center atom, which is the important guy here, the first thing we want to identify is how many electron pairs there are. And in this case, there is 1 electron pair there and 1 there. It has 2 electron pairs. Once you see something with 2 electron pairs, the electron pair geometry name will be linear as well in this case. Now, when we look at 2 electron pairs, we also want to count up how many bonds there are. There's 1 bond there and 2 bonds there. So it has 2 bonds. So in this particular case, what we got going on is we have these 2 bonded pairs, which really don't want to be near each other. So they're basically going to get as far away as possible from each other. So in this case, because there's only 2 bonds, they could basically end up on opposite ends of the central atom, basically 180 degrees apart from each other, and they end up with a molecular geometry that is known also as linear. So they are both linear, the names here. One again describes how the electron pairs are arranged. One describes how the overall geometry is, and the bond angle is 180 degrees from each other. Again, this situation, because there's no other bonds or anything in the way, they could clearly get as far away as possible from each other. The result of that is it just basically ends up as a sort of a straight line that occurs there. Any question on that one there? Yeah. They will not. So in this particular case, as we can see here, and what we will see is when you count up the number of electron pairs, actually, I'll word it differently. When you draw your Lewis structure and you have no non-bonding electron or dots on your central atom, both names will be the same always. So these 2 names will always be the same when you draw your Lewis structure and there's no dots. And the reason for that is the only type of electrons that are involved in these type of molecules are bonding electrons, which means they're basically holding on to atoms, and those are the only electrons. So wherever they end up, the electrons and the atoms end up basically in the same geometry because those are the only ones that are involved. So they always will end up being the same name when you draw the Lewis structure and no dots on the center atom. It will not matter because they're considered to basically to be one electron pair or one bond. So as long as there are no dots on the central atom, both of those names will be the same. Yeah. Other questions? Let's take a look at the next example, which is basically a central atom with 3 things attached. And again, if we look at our boron here, it has 1 electron pair, 2 electron pairs, 3 electron pairs. It also has 1, 2, 3 bonds in this case. Something with 3 electron pairs, the electron pair geometry is what is known as trigonal planar, or some people will call it triangular. Now with 3 electron pairs and now 3 bonds and actually 1 extra atom in the bonding situation as compared to the previous one. Now what happens is as those 2 guys try to get away from each other, there's a 3rd guy in the way, right? It's got to move with it. So what ends up happening is they try to space themselves as best as they can away from each other. And we end up with a molecular geometry or shape also of trigonal planar. So again, here, when we look at our Lewis structure, there are no dots on the central atom. Both of these names are identical to each other. Again, because the only electrons we're dealing with are bonding electrons. So as those bonding electrons move, so does the atom, and the overall shape basically stays the same wherever they end up. It is called triangular or trigonal planar because essentially it makes a really badly drawn here triangle, right? Makes a nice equilateral triangle basically in 3-dimensional space, has a bond angle of about 120 degrees apart in that particular case. Any questions so far? The next example is a central atom with 4 things attached, and that's a really messed up picture of it. All right. Redraw it here. So it should look like this. There we go. Now, when we look at the central atom, which again is the carbon in this case, it has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs here. It also has 4 bonds, the same things are all bonds as well. Something with 4 electron pairs, the electron pair geometry name is what is known as tetrahedral. The molecular geometry name, again, will be exactly the same because they are all the same bond. Everybody's on there together, and it will also be tetrahedral. Again, there are no dots on the central atom, so both of these names are the same. As I mentioned in the last 2, the bonding electrons are moving with the stuff attached, so they end up in the same geometry of each of them. In this case, unlike the trigonal planar, we end up with 4 things attached, which means 4 things are trying to space themselves out as far as possible. And we do end up with this tetrahedral shape, which has a bond angle about 109.5. On the face of it, it kind of makes a triangle, and then kind of on the bottom, it makes more like a pyramidal type shape in that type of geometry. So again here, no dots on the central atom, basically no non-bonding electrons. Both names are the same because again, we're only dealing with bonding electrons interacting with other bonding electrons. And again, as those atoms move, that's basically how the electrons are moving in this case. Any questions up to there? So when does the names really change? The names really do change when we start introducing non-bonding electrons on the central atom, those dots on the central atom. And it's really because of the interactions that occur when that happens. they are electrons. So the best situation that you could have in terms of we will tolerate each other is what we just went through, bonding electrons near bonding electrons. That's sort of the best situation. The next best situation is a situation where you have non-bonding electrons near bonding electrons. That's basically dots near lines. Not so great, not really happy about that. They want to kind of get away from each other. The worst situation that could occur in terms of a bonding situation is non-bonding electrons near non-bonding electrons, dots near dots. They really don't want to be near each other. So what ends up happening is the only way we really sort of get dots on the central atom is we actually don't have a bond happening at that spot. Because we don't have a bond that's happening at that spot, there's like an empty void at that point where the non-bonding electrons can actually move and the bonded electrons can move with their things. And there's a little bit more room for everybody to spread out because we're missing that like third bond or fourth bond that normally would be there. So because these non-bonding electrons are there, it allows the overall guys to really spread out a little bit more. And what that really affects is only actually one of the names. It actually only affects the molecular geometry name. So that is the name that actually changes when we start introducing non-bonding electrons. The electron pair name is actually still the same because there's still the same number of electron pairs. They just happen to be non-bonding electrons versus bonding electrons in this particular case. But the molecular geometry name will adjust because of that extra room. The overall shape of it is able to sort of move a little bit more. So let's take a look at this here. Sulfur dioxide is an example of that. And if we drew sulfur dioxide, it will look something like this. So in this particular case, we are going to look at the central atom, which is the sulfur here. This sulfur has how many electron pairs around the central atom? It does have 3. It has 1 here. It has 1 here. Doesn't matter if they're lines or dots. And our double bond only counts as 1. So this is 3 electron pairs. In terms of bonds, it has 1. And again, the double bond only counts as 1 as well. So it has only 2 bonds. So that is basically what we're looking at in this situation. As I mentioned before, the number of electron pairs determines the electron pair geometry, and that name doesn't change. So as we saw earlier, the electron pair geometry for anything that has 3 electron pairs is still trigonal planar. But what happens in this situation is these non-bonding electrons decide, I would like to go away from you guys. The result of that is these oxygens will come down and go, I want to get away from you as well. And what ends up happening is we get a molecular geometry that is known as angular. Some people might call it bent angular. Some people might just call it bent. And basically what ends up happening is the molecule sort of basically angles like this. And it has a bond angle of less than 120 degrees. The bond angle is based on the electron pair geometry. So trigonal planar is 120 degrees. Because of the non-bonding electrons, it comes out a little bit less than 120 degrees because of the extra sort of movement that can occur in this particular case. Any questions on that there? And in this case, the reason for that is we have the bonding electrons near bonding, and then we have the non-bonding electrons near bonding, which is, again, not a great situation. The next example is something like NH3. If we draw NH3, we end up with something like this. Looking at our central atom, which is the nitrogen here, it has 1 electron pair, 2 electron pairs, 3 electron pairs, and again, 4 electron pairs. It also only has, in this case, 1, 2, 3 bonds. So something with 4 electron pairs, the electron pair geometry is still going to be tetrahedral. Again, in this case, we got a couple of situations occurring. We got our bonding electrons near non-bonding electrons, bonding electrons near bonding electrons, same situation. These sort of non-bonding electrons go up. That causes all these guys to kind of come down. And we end up with a molecular geometry known as trigonal pyramid. And I just heard somebody say they saw it. So this is what we got, kind of like a triangle shape that becomes kind of pyramidal on the bottom is essentially what happens in this particular case. And that is really where the name comes from. The bond angle here is still based off of the tetrahedral because of the non-bonding electrons. The bond angle is less than 109.5. And it's approximately like 107-ish in that ballpark, 104. Let's take a second to talk about this name here. That's trigonal pyramid, and a name that we saw earlier, which was trigonal planar, right? Trigonal planar is 3 electron pairs and 3 bonds. These are 2 different things, yes? So when you're giving your answer, do not just write trigonal and let me choose, because I will choose with an X, yes? So make sure you choose trigonal planar or trigonal pyramid. Don't do my other favorite thing. It is trigonal. Was it pyramid? Clearly that says pyramid. That is clearly what that says and stuff. So, do make sure you choose. A very common thing people do is just lay up trigonal and hope for the best. You got to pick one of them. They do mean obviously 2 different things. Any questions on that there? Yes. You don't really for me. I don't know. Maybe it'll be an extra credit question on the exam or something. But other than that, probably not. Yeah. Other questions? All right, one last geometry that we cover in here, because we don't get into those expanded octets. If you plan on continuing to take chemistry, you'll be very disappointed. There's a lot of geometries that go with those expanded octets. But since we don't do that, that's good. Here we have water, so we're looking at oxygen in the center. It's got 1 electron pair, 2 electron pairs, 3 electron pairs, and lucky number 4 there. That is 4 electron pairs. In this case, it has actually only 2 bonds, 1 bond there and 2 bonds there. So that is 2 bonds. Same deal in this situation, the electron pair geometry, because it has 4 bonds, will be tetrahedral. This is a case where we got the worst situation happening of everything. We got all 3 interactions happening. There's bonding electrons near bonding. There's non-bonding electrons near bonding. And the worst situation is non-bonding electrons near non-bonding electrons. So what ends up happening, because we have the 2 pairs of non-bonding electrons, there's a lot of space for those guys to move out. So as these non-bonding electrons kind of move up, it causes these hydrogens basically to come down out of the way. And we end up with a molecular geometry known as bent or V-shaped. That's why oftentimes you do see water drawn like this, basically like a upside down V or bent type of thing. It has a bond angle also based off a tetrahedral here. It is also less than about 109.5. This guy's about a 104-ish in that real ballpark. Question on that there. Yeah.
Would it be wrong to then simply see
It would be if your question on this one here, to use V-shaped would be wrong. That's why personally, why don't we just make it simple? We'll go for here in lecture with angular for this one, okay? And the reason I do that is there are people that will use bent for this one, and like I said, some people will use bent angular for this one. But there is really a difference in terms of the bond angle of the two. This one's only just a little less than 120. The other guy is less than like 109. So it's a little bit more of a drastic one, which is why they sometimes will use V shape for the water versus this one. This one's a little bit softer of an angle, if you will. And that's why sometimes people will use angular. So for us, just to keep it so there's no misunderstanding, if it is this situation where you have 3 electron pairs and 2 bonds, we'll go strictly with angular. And if it's basically like in water, 4 electron pairs and 2 bonds, we'll do bent or V-shaped, and we'll just keep it like that. That way, everybody's on the same page, hopefully on that. Yep. Other questions on that? So like I said, truthfully, memorization is sort of the best way. And, I usually like make a table, like looking at the central atom, the number of electron pairs like we did. And then the number of bonds. And then that's going to give you your 2 names, your electron pair geometry name and your molecular geometry name or your shape. So basically 2 electron pairs, 2 bonds, that is going to be linear on both of these guys. 3 electron pairs and 3 bonds, that's going to be trigonal planar on both of these. Four electron pairs and 4 bonds, that's going to be tetrahedral on both of these. And obviously this is a central atom, and looking at the central atom. Now, up until this point, when you would draw your Lewis structure, there would be no dots on the center atom. So the central atom should have no dots. Both of the names would be the same. Then we get into our 3 electron pairs and only 2 bonds, like the SO2 that we were just talking about. 3 electron pairs would be trigonal planar. And that would be our angular. 4 electron pairs and 3 bonds. 4 electron pairs would be tetrahedral. And that would be our trigonal pyramid. And 4 electron pairs and 2 bonds would be our tetrahedral. And for the shape would be our bent, our V-shaped. And obviously on these guys, you have dots, right, on the central atom. And that is where we see the 2 names basically be different. So this is a good little table to kind of just memorize. And all you have to do, obviously, is just go to the central atom and count the number of electron pairs. And again, as I mentioned, that is the key. It is the central atom that you want to look at. And, sometimes people don't go to the central atom to do that. This is obviously, just so we're clear, this table is for when you have 3 or more atoms, that are involved. Obviously, if you have a diatomic molecule, as we talked about earlier, it is always going to be linear, no matter what the situation is. There's really no central atom, so there's really just one name associated with it, which is just linear. And again, that would be just if you just had, obviously, 2 things only. Any questions on that there? So if we go back and take a peek here at some of the stuff that we drew before, or actually I'll do it, I think, on the next page. I'll just redraw some of them. So we had this guy. We also drew, I think, this guy earlier. We drew this guy. We did this guy. We also did this guy. We did this guy. Okay, so why don't you take a minute or two, and for each of these, determine the electron pair geometry and the molecular geometry. And again, the easy way, go to the center atom, use that table we just talked about, which is basically what we did on each of those slides. And you should be able to come up with the names pretty quickly, hopefully. Let's take a look. So I'm going to start with number 1. I see 3 or more atoms. So I am always going to go to the center atom. It's always where you want to go when you're doing geometry. And there's really 2 things I'm interested in. I want to know basically how many electron pairs are there around it. How many electron pairs are around that carbon? So it is actually, in the case of geometry, only 3. It is the single bond, and remember, double and triple bonds count as only 1 electron pair for geometry. So it basically has 3 electron pairs. Really, that is all you need to figure out the electron pair geometry. You could roll back to our chart, and I see 3 electron pairs, means the electron pair geometry is going to be trigonal planar. So that's what would the electron geometry would be trigonal planar for this guy. Now, how many bonds does this guy have? This guy has 3 bonds, a single bond, double bond counts as 1, and 1 more single bond is 3 bonds. I can now go back to my table and find 3 and 3. The molecular geometry will also be trigonal planar, because when we look at this, there are no dots on the central atom, which automatically tells us that both of these names should be the exact same. Question on that one? Looking at number 2, again, I got 3 or more atoms. I'm going to go to my central atom. You're going to tell me the total number of electron pairs based on geometry is how many? It is 2. Each double bond only counts as 1 each. Number of bonds would also be 2. Again, I can roll back to my table. 2 electron pairs and 2 bonds means my electron pair geometry is linear. No dots on that central atom means both of them are going to be the exact same name here. They both will be giant. No, they both will be here linear in this case. Question on that? Yes.
So you're saying that if there's no like electron pairs on the atom itself,
Yeah, if there are no technically non-bonding electrons, which on your Lewis structure are dots. So basically, if there's no dots on the central atom, which means there's no non-bonding electrons. The only type of electrons you really have are the bonding electrons. So because they're within a bond, they basically are holding on to the atoms in the bond. So as they move and wherever they end up, so does the atoms. And that's really why both of those names are exactly the same, because the only things moving are the things with the atoms, and the electrons are also moving in the same exact spots. So that's why they're exactly the same. Other questions? Number 3, how many electron pairs on number 3? The central atom here would be sulfur. It is, how many electron pairs? It is 4. Remember, we don't care if they're dots. We don't care if they're lines. We just want to know how many electron pairs there are. And in terms of bonds, there are 2. So we can roll back to our table. I got a choice of a lot of 4 electron pairs, but I'm looking for the combination of 4 electron pairs and 2 bonds. Now, 4 electron pairs, no matter which one you choose over here, they all have the exact same name for the electron pair geometry, because there's 4 electron pairs. It will be tetrahedral. But in this particular case, we actually have 2 non-bonding electrons there, which gives everybody a little bit more room to spread out. And what ends up happening again is we end up with this bent or V-shaped, because there's a lot more room for those guys to move around. So this will be tetrahedral for the electron pair geometry for this guy, because of those non-bonding electrons. This is exactly like water, this guy. He basically has those 2 non-bonding electrons I want to get as far away as possible. When it does, again, the hydrogens come down, and we end up with bent or V-shaped here for our shape. Any questions on that one there? All right, number 4 here, how many electron pairs? 4 has actually 2 electron pairs. one electron pair here. Triple bond only counts as one, so that is two. How many bonds? It is two in terms of geometry. Same two. Are there any dots on the central atom here? Should these names be different or the same? They should be the same. So we could just roll back to our table, two electron pairs, two dots. This one also is going to be linear for both of them. Any questions on that one? Number 5, there is no central atom. It is only a thing of two, which means the geometry is linear no matter what it is. Really doesn't fall into either of those categories. So we'll just call the geometry as linear because there's really no central atom. There's really no bond angle or anything happening. So the overall geometry here would really just be linear. I'll write it through both boxes. Last one here is our sulfur electron pairs here is 4. Bonds is 4. Different names or same names? Same, because there's no dots, right? So we just want to go back to our table. I see a lot of 4s, but that's a 4 and a 4, and that's going to be tetrahedral on both of them. It's going to make that 109.5 degrees. Any questions on how to do geometry? Simplest way is really just memorize that table and count up the electron pairs. Now, you can, for example, let's say we had something like this, which in labs, they sometimes like to give you guys like a lot of organic things to draw. Was that one of them? No? Oh, so in this particular case, there's actually multiple central atoms, kind of like I think we drew nitric acid, I think the other day we did, right? So, you know, if we drew the nitric acid, it looked like this. Right. So there are times when you do come across, you know, multiple central atoms. In the case of the guy on the left there, carbon's a central atom and oxygen's a central atom. And you could do geometry really for both of them separately. So you would go, okay, I'm going to do the geometry, say, for the carbon first. And basically what you would do is, I can't really do it on here, but you basically, as I mentioned before, kind of what I just put in a box, you kind of put your hand over the stuff in the box and you look at just the carbon, but the bond and everything here still counts for the carbon. So if we looked at the carbon, how many electron pairs would it have? It would have 4. How many bonds? Which means if we're going to do just the molecular geometry here, it should be tetrahedral, all right? Actually, it'll be tetrahedral for both, but the molecular geometry here would be it. Once you're done with that, then you kind of do the opposite, put your hand on that box. And again, the bond here would go to the oxygen. So when we look at the oxygen, how many electron pairs? Yep, it has 4. How many bonds? It has only 1 and 2. So something with 4 electron pairs and 2 bonds, the molecular geometry would be bent or V-shaped, yeah. So if you actually built this model, you would see a guy here that is sort of tetrahedral going into like a bent or V-shaped here, and this guy would have kind of that, you know, tetrahedral sort of arrangement that happens on that side of it. You could obviously do the same thing for the nitric acid by just isolating the nitrogen here. Electron pairs on nitrogen would be 3, 1 here, 2 here, 3 here, and 3 bonds, right? Which means the molecular geometry for this nitrogen would be trigonal planar, right? It makes like a triangle on this side. Then you would do the same thing with the oxygen, which will be identical to the guy on the left there, and you'll have a bent or V shape. So you can apply geometry to multiple central atoms. You essentially just kind of put your hand over one side and do it for the other. Question on geometry here. All right, we're laid up there. We got one more little bit to talk about.